All right. Welcome everyone to the October 2022 edition of What's a Microcontroller with Python and the Microbit. This is an electronics class that uses the microbit as its programmable brain. Here is a link to this slideshow. You can type it in, or when you go to YouTube, you will see under the Show More button, you'll be able to go to this link. So if you're watching this from YouTube, just look below the video and there will be a link to this slideshow. And I will go ahead and paste this in. This slideshow has lots of good links that that you may want to refer back to. So I'll be also sending it in follow-up emails and stuff like that. Okay, so there is a link to the slideshow. You're welcome to just go to it and watch along. Like I said, the most important thing is that there will be links that I follow during this presentation that you might end up wanting to revisit later. And so the links will be in here for you. With you today are me, our company vice president, Ari Alvarez, and Stephanie Lindsay, who is hosting today. Thank you, Stephanie. Stephanie, by the way, is our product and documentation manager. And then there's me. My background is in electronics, and in addition to working on supply chain stuff and making sure that all the educational kit parts work as expected, I've been working most recently on the Cyberbot robot and this electronics kit. And I put some links to some earlier YouTube versions of these workshops in case you want to look at any of those. We are Parallax, just outside of Sacramento, California, in the middle of the state, 20 employees, and we've been in business since 1988 and doing educational products and curricula since 1997. Fundamentally, Parallax is about development with electronics, and in modern devices, be they commercial devices or prototypes, there is some kind of programmable, usually a microcontroller inside there that has a program. It's connected to a bunch of circuits inside the device. And so, for example, in the microwave oven, when you press a button on the microwave oven, you hear a beep. Well, that's because the microcontroller, which is connected to the buttons on the microwave oven, detected a circuit change, and then it knew to send rapid high-low signals to a speaker at an audio in the audio range to make it beep. And then the microcontroller pretty much does everything else to make your microwave go. Increasingly, some of these devices are now seeing full-blown computers, as they are tend to be things on the internet as well. Hopefully not our microwave, but let me know if any of you have a Internet of Things microwave. We don't. Chip Gracie is Parallax's chief inventor, and Ken Gracie is the company's CEO. These two guys have been shaping Parallax Chip with great inventions, and Ken is actually the one who got the education program started back in the late 90s. One of the things that Chip did in the late 90s was develop the Basic Stamp 2. And this is the thing that really got programmable devices in electronics started for students and hobbyists. Before this, it took a very high level of electrical and electronic technical understanding to program a device, connect circuits to it, and make it work, as in make it work in any of these kind of applications. And the Basic Stamp was the first easy to program, easy to get started with device. And so it really took the hobby and education world by storm, and a lot of things changed. Now, there have been several iterations of new popular microcontrollers that are used in electronics. And the most recent one is the microbit. And the microbit is very popular for good reason. It has lots of great built-in features for students to just have a great time. And so they can write a program to make a little beating heart or an emotion badge where they can press a button and pick a smiley or a frowny face. Step counter is one of my favorite. It even has a built-in compass and a built-in radio so that you can do things like send one of your classmates a smile. And these kind of applications, these kind of microbit only applications are available through the Make It Code It website. And so if you want to do something just to warm up with your students before or possibly in an earlier class, these are some things that they can try out. And just to show you, like if we want to do a beating heart, for example, I just clicked the beating heart on the previous page. So here we are. I'm clicking beating heart, and then now we have a quick little how it works video. And you'll be initially presented with block programming, which is perfectly fine. You can do this in blocks, or there's also, there's a make code option. So these are make code blocks. And then there's also a Python option. And when you click that, it'll show you the MicroPython version of that same code. And this is the language we'll be using today. And you can even open it in the Python editor. Now, this is taking us to the very latest editor, the version 3 editor. It's got some great features which we can talk about, but since there's an entire student workbook of tutorials that currently have the version 2 editor. So this is python.microbit.org/v/3, and then we'll be using python.microbit.org/v/2, which looks like this. And let's see here. So if I need to backtrack a little bit. So if we go to the beating heart, another way you can do it is look at the Python and simply grab the text if you're using the version 2. Paste. So then we have the code for the heartbeat, and I'll go ahead and paste that into your into the chat. And I'd like you all to basically, while I'm speaking, get your microbit connected over USB and try to make sure that this runs in the /v/2 editor. Actually, let's see. So I'll paste in the code, and then I will paste in the editor address. So there is the code.
And can we also take a moment to make sure everyone can see Andy's screen? We have some folks who are saying they cannot see your screen.
Okay.
I know of one person I'm seeing. Can we get thumbs up if everyone can see the screen?
Okay.
I'm getting lots of thumbs up. If you aren't, you might want to hit escape, and then some view options might appear, or right click on what you can see and look at view options for anyone who's having trouble. Okay, I don't think anyone else is having difficulties, so go ahead and I'll address this with one person.
Okay.
Thanks.
Thank you. All right, so that is just a quick example of some fun stuff that you can do with the microbit on its own. And there's really quite a lot. For example, back at the Make It Code It site, and again, that's this link right here, Make It Code It. microbit.org/projects/make-it-code-it is where I am. And you can, for example, select your programming language as Python, and you can essentially narrow the search. For example, Maybe we want to use the push buttons that are built into the microbit. Well, here are the push button ones. Or maybe we want to look at what we can do with the built-in accelerometer, like the step counter. So these are all ways you can use the Make a Code It site as a kind of a warm-up thing and to prompt some student enthusiasm. And additionally, if you'd like to see more information like that, I put a slide with two 2-hour sessions of microbit only activities where we explore resources like that one and including that one. So if you're interested in having a microbit only section, I highly recommend the YouTube recording of this workshop. And with all that, today we will be doing intros and overview, which we are in the midst of. And after that, we'll review the homework. I'm going to try to go through it at light speed so that we can get to the, well, I'm going to go through that as quickly as I can so that we can get to the projects, which are the main part of this workshop session. But yeah, I want to talk about the homework because one, maybe some questions will go up as we're reviewing it. And then two, it's good for folks who might not have been able to join us today, but we'll be catching up later on YouTube, which you'll be able to do. We typically get the video up about 3 hours after the session ends. So usually around 8 or 9 o'clock California time, PM, it'll be up same day. So then we'll be taking our electronics prototyping kit and getting it set up and test. And I'll show you how we introduce electrical continuity to the students. And if time permits, we'll also build and test a light. For homework, you'll be building several LED lights and also some push buttons like the one, these are the LEDs you'll find on the microbit and the push buttons you'll find on the microbit, but it's nice to have the experience of building something that you're somewhat familiar with, but in a kind of a new way. And so that's where the LEDs and push buttons are going to become important. Plus they open up a lot of opportunities to learn about circuits. And there's a lot of learning about circuits in What's a Microcontroller with Python and the microbit. On Wednesday, we'll be experimenting with those circuits and then hopefully building a servo. Along the way, we'll be learning quite a number of computer science and electronics concepts. And then on Friday, we'll continue with a few more projects with the potentiometer. That's a dial you can twist. We'll look at some additional activities and the teaching materials, cyber.org curricula, and some of the related robots, kits, and other things that you can do with the microbit that we have student workbooks and teacher resources for. Are there any questions before I move on? Okay, well, just so you know, it's always fine to unmute yourself and say, hey, Andy, I have a question. Stephanie and Ari will also be watching the chat for questions if you'd prefer to just put in a question in the chat. Sometimes they bring it to my attention because it's a question that they think everybody ought to hear the answer to. So those are your ways of getting your questions answered as we go. So here is the complete kit. Some of you, thank you if you already had a microbit and a serial cable. We really appreciate your volunteering to get the rest of the kit without the microbit included, because there has been a big shortage up until just recently, and I have a big announcement about that in a couple of slides. So here is an example of the electronics kit being utilized with a whole bunch of different circuits. There's some additional indicator lights, push buttons. This is called a potentiometer. It's a dial or a knob you can twist and then to adjust stuff. There's a piezo speaker up here. That's actually not in the kit. Light sensor, and then a servo which can control position. And the servo needs a battery pack. So this is the kind of, you can really get involved, as opposed to the microbit does have some spots where you can clip on alligator clips for 1 or 2 circuits. What this kit does is it expands your options for exploring into electronics more deeply after possibly doing some of those alligator clip exercises. One of the reasons that this is important, and this the development of this kit and its material was funded in part by cyber.org. We have a link right down here to their website, is that there's been a lot of discussion about reshoring. So for example, there's a lot of funding available to integrated circuit manufacturers to come back and open up campuses in the United States for development and manufacturing. And so the kind of lessons that are in here, we hope will spark interest in a certain number of students and get them to want to go that kind of direction with their studies. And also it'll be important to them because they will have some additional background that other students may not have had in electronics at an earlier high school and junior high school level. We're estimating that to go through everything in a high level of detail, it's about 40 hours of study or 40 class hours. And but you can also pick and choose certain activities that are maybe more rewarding and less pre-engineering oriented. So we tried to put most of the STEM and fun, just sort of try it and see how it works things at the beginning of the chapter, and then near the end of the chapter, there's usually kind of a deeper dive into certain topics. The main place for both student and educator resources that Parallax offers is called learn.parallax.com. And I'll go ahead and follow that link. So here we are at learn.parallax.com. And it'll probably look a little bit more like this if you go to it on your screen. And what we show on the landing page is primarily student resources. And for example, here we have what's a microcontroller with Python and the microbit. And that's going to be the student workbook that we are working on today. And then here are the chapters, if you will, within that student workshop workbook. The proper name, correct me if I'm wrong, Stephanie, is that each of these are actually books. I would consider them to be more like booklets, but
sure. Tutorials. Yeah, but we do call it a bookshelf, sort of, because you see the different categories grouped together.
Yes, and I think that's also the nomenclature of the actual site itself is, and so this is my recommendation would be to think about each of these tiles as the entry point to a chapter about something. And then, of course, this is the workbook in its entirety. And notice also that we have a Cyberbot robot under Python and some cybersecurity lessons as well. So again, this is the student workbook. I put the link in. You can either usually click a picture and get there. So it's built into the slideshow, or here's the link right down below as well. Educator resources are also at learn.parallax.com. And we will go, we'll take a closer look at those on Friday. But for now, just know that they're there. And if you already have a login for learn.parallax.com, you'll be able to get to these educator resources. And then for those of you who don't, we'll be sending out an email during the Wednesday class so you can get signed up and then be ready for Friday, able to look at the resources. It won't be necessarily required though. If you can't, I'll be demonstrating and showing all the resources. So there won't be anything lost if you're not able to get in by Friday with the instructions that we send out. There's always a few people who end up either not getting the email because of a spam filter or, little things like that can happen. And so I just wanted to mention ahead of time, don't worry if you can't get it all set up by Friday, if you're the one or two people that it happens to. But yeah, if you don't have a learn.parallax.com teacher login, we will send you one before Friday. And so going to learn.parallax.com/educators, handily, what's a microcontroller with Python and the microbit resources is the first link. And again, we'll be looking more closely at this on Friday, but for now, I just want to mention that right now, students cannot get to the assessment materials because those assessment materials have solutions to them. There are answered student practice materials in every activity, but there's a second set for you with solutions in this area once you follow the login and go ahead and log in. Outside of the area, we have the slideshow that I already shared the link to, and some additional resources here. And again, I'll look at this in more detail on Friday, but did want to mention it up front. For purchasing what's a microcontroller type materials, I went ahead and included a slide with a link. And we now have microbit Go kits in stock. There's been a long dry spell of just pure microbits. But before I go there, so the what's a microcontroller, we have a 12-pack package of kits, as well as a version with no microbit if you already have a whole bunch. We have a refresher pack of parts for the small electrical parts if they're damaged or lost. It's nice to have a few of these on hand. And then, of course, the one that most of you probably received, which is the electronics kit plus the microbit. And now, additionally, if we just go back to parallax.com and go to shop, along the left-hand side, where'd it go? Microbit, there it is. So we have a microbit category here, so you can buy the modules on their own. You can also buy the kits. So we have 9 microbit kits. And so the club bundle is in stock. That's, I believe, is it 10 microbit kits in a club?
Yes.
Thank you, Stephanie. And then there's also the Go bundle, which is right here.
Which we have in stock.
Yes. Yeah. So with the supply chain being what it's been over the last couple of years, there have been dry spells where the microbit has not been available, and we just got them back in stock. So if you need to stock up on some, I would recommend doing a purchase order as quickly as possible, because I don't know how long they last. But then again, I'm a tech, so I have no actual information on whether they last a long time or not. But since they've been out of stock for so long, I would certainly recommend getting them if you can, if you need them, and if you can at this point. Okay, so next up is the homework. This is where I'm going to talk a little bit about what you went through as quickly as I can. So here is the homework where you went through and tested your microbit connection. Maybe I don't want to do that. I'll do it over here, 200%. And so this was step by step with a video, and this is kind of a condensed version, getting you ready for this workshop. It's a very fast forward. Okay, grab your microbit, connect it to your computer, hit the connect button. It'll present you with a list of microbits, of which you only have one connected, but you still have to select that, and then hit connect. And then it'll show you one that you have the option of now disconnecting, and also that you can now flash the program directly to the microbit. And after doing so with the test program, you were able to type in a message, and then it repeated the message back to you. And that pretty much just gives you confirmation that, hey, your microbit and your computer are playing nice for all the things you're going to do at the workshop. We also had a test of the cyberscope. Where'd that go? Yeah, here are the cyberscope tests. And so the cyberscope's kind of fun. And we'll be using it quite a bit. On the second slide here on the landing page, there is a little video. And what that video does is it shows you step by step, if you wanted to try it, how to right-click, try cyberscope.hex right there, and then download it, and then go to python.microbit.org, and then drag and drop that hex file from your downloads and drop it into the load save window, and then load that into your microbit. And after loading it into your microbit, hit disconnect, then go to the cyberscope and hit connect there. You'll also have to choose your microbit and then confirm connection. And what it's going to do is it's going to send, it sends data, voltage measurement data, although it's not actually measuring voltage. It's currently, we will measure voltage today, but this demo is just basically taking a bunch of, or sending a bunch of voltage measurements as though they were measured. And so this is the oscilloscope part where you can look at voltages inside circuits as they vary with time. Now we also have in the cyberscope very standard features like measuring voltage, resistance, and current. And then there's a bunch of lessons that go along with that. And so that is the cyberscope. Now, additionally, we had a quick little how to save and reopen a script. Now, the link that you followed is another Google Doc, but what I want to emphasize with all these homework assignments is that the students just simply have a more step-by-step version of this because you know, we have time constraints during this workshop, and so we're trying to do it on kind of a fast track. But if we were to go to learn.parallax.com and then go down to what's a microcontroller with the microbit, notice that there is now, we actually added that the contents of that Google Doc to the bookshelf, i.e. chapter list. And so now you can actually go, or your students will go through that activity. And it's a very important activity so that they understand how to save hex files. And we'll actually be doing that shortly. For connecting your microbit, there's the software and setup for microbit, the very first one. And this is where we talk about, okay, you can use the online Python editor or something called the Mu editor. The Mu editor has been a little bit, success has not been as good with it as with the online Python editor. The Mu editor kind of varies with computer, whereas the online Python editor, it works with Chromebooks, Macs, and Windows machines. And also reportedly on Linux boxes. So this is, and with very little in the way of hurdles to get things up and running. In fact, less than with any other microcontroller system I've ever used. So when we talk about installing software, you have to make sure you have a Chrome browser, but after that, all you have to do is follow the link and here you are, and here's the software. And again, it's going to say, hey, why don't you try version 3? And for these tutorials, until we update to support the version 3 software, let's keep using version 2. And again, that's python.microbit.org/v/2. Okay, and with that, what I'd like to do is just give you a quick example of a lot of this stuff kind of condensed. So the first thing I'm going to do is paste in a program. And what this program is it's essentially all of these homework assignments that you either looked at because you're familiar with MicroPython, or you maybe set your screen side by side with the tutorial. So for example, here we have making decisions. So that would have been the 4th page you visited in the online tutorials for the students. And it introduces the idea of making decisions and then how that works in MicroPython. And we had you try out this program right here. And what I recommend to teachers who have not tried MicroPython before, or who want to gain some familiarity with it, is to actually put that tutorial up on the left window. So for example, make decisions. Go ahead and copy that link and then paste it over here. And it doesn't necessarily have to be the left window. That's just my habit. So here we have our, an activity within a chapter within the textbook on making decisions, a fundamental computer science standards alignment concept. And over here, you'd have your python.microbit.org/v/2 editor. I accidentally went to v3. Okay, and again, we're not gonna try out 3 because version 2 is what's fully supported, and we're thinking about when to schedule an update to the version 3. But version 2 is still very good. It's going to be around for a while, and so it completely works. It's better supported. You can do everything in version 3, but the buttons and the instructions are slightly different. All right, so for making decisions, if you're going to be going through a tutorial, and especially for your students, the thing that can end up really derailing the ability to learn the language is to do what I'm doing right now, which is to copy and paste into the editor. To really learn the language and to be able to do okay on the quizzes and things like that, it's much better to actually start from scratch and say, okay, simple underscore decision dot py from microbit import star a equals 89, b equals 42. Gee, I wonder what we're going to do with that. Oh, let's see here. Okay, so it says right here, if a is greater than b, if a is greater than b, colon, and then display dot scroll, a is greater than b. Now, I don't usually have issue with noticing, oh, wow, gee, that's pretty similar. So I could, as a student, potentially copy and paste the existing code and then adjust it to being like the new code. That is perfectly fine. Because it's a sign that the students are still involved with what they're doing, to have noticed that. And so this example, then you get it typed in and you can go ahead and run it and verify that in this case, it displays this, and then try rerunning it with maybe B changed to something larger than A, and then verify that it does that, and then move on. And try the next one. And then here we have a more complete one where it recognizes, hey, it can be greater, it can be less, it can be equal. And that's what we try to do in these tutorials, is also kind of take a step-by-step approach where they don't have to take too large of a step to see the next thing in the progression of how a script would work. And let's see here. So that's an example of how to learn MicroPython. So if you're very new to MicroPython and you feel overwhelmed, one of the things to do to gain more confidence with it is I had you do just excerpts, the kind of the minimal from each of these chapters. But you can go through here line by line if you really want to learn Python or the very basics of Python better. This is a good step-by-step tutorial for that. Keep on doing a Windows keystroke that accidentally opens the emoji list on my Mac. Sorry about that. Okay. So one other thing is I put a slightly older but longer and more step-by-step document that goes through the same things I just whizzed through. There's a video and like I said, a larger document available for that. And now what I'm going to do is go back to the idea that, hey, we have this list of concepts and let's just really quick talk about those and actually run this script. So now I'm going to paste this into you. So here is the script for you to paste into your python.microbit.org/v/2 editor. And so let's see here. I just realized I didn't connect my microbit. Might as well just document the whole experience. Okay, so. And by the way, it is also best to have your Zoom not filling your entire screen unless you have more than one screen. That way you can have Zoom watching me over here and then possibly be making adjustments to whatever script we're doing on this side. So where I have a picture of my microbit kit, you might want to have just your Zoom or the ability to go from full screen. And Stephanie, can you describe for them how to switch from full screen to a window so that they can arrange it with their python.microbit.org editor? I believe that the choices are in the upper right of your Zoom window. Maybe Ari, there should be like
okay, Stephanie, go ahead.
Oh, if you're looking at Andy's presentation and it's filling your whole screen, you can hit escape and then view options drop down menu will show at the top. And
so escape, view options.
Yeah, and you can also on your other pane there in the upper left, there's a view button with a grid, and you can switch from a speaker to gallery to full screen view there.
Okay, thank you very much. And sorry for not warning you ahead of time about that request.
Yeah.
All right, so here we are, and I'll go ahead and just recount the other thing that you all did, which was at the very beginning, which was to open up your box, grab your serial cable, and then looking further in here, there should be a microbit Go bundle. Inside there, it's going to be a security sticker that's really tough to get through. And here is your microbit. Now, there is also a battery pack and batteries. You want to make sure to have those ready for Wednesday, although it depends whether I'm not sure whether we'll be using those Wednesday or Friday. We'll see. This shorter serial cable, or the shorter USB cable rather, is good to have, but the longer one is recommended for what we're going to be doing, since you'll need to have your microbit and the electronics prototyping stuff in a comfortable spot. All right, so here we go. So we'll start out by just getting our microbit going, and then I'll run that sample program. So connect to the microbit, and then connect the other end to a USB port on my computer. And everybody remember that, where the microbit did its sort of preloaded out of the box program. So after doing this, we should be able to hit connect, and it'll list a BBC microbit, which you can select and then hit connect. And then in this case, we'll flash this, this program. And because it's the first time it's loading the latest microbit runtime onto the microbit, which is why it takes a little bit longer for it to complete. I can hear my CPU fan getting faster and faster, so I'm going to mute my video so that we can see my see the video on the document camera instead.
Okay, we are getting questions. I'm
All
not getting
right.
flashing anymore. How do I reset?
Okay, so the main thing is, can you connect and disconnect here? Because the first thing we want to do is, you've got your microbit, and you want to be able to, let's say I'm unplugged here, and you guys have all run some kind of example program. And when you plug back in, make sure that you're plugged in well so that you can see the red and amber lights that are by the USB connector on the microbit. And then, of course, make sure the other end is well connected to your computer as well. And then when you click the connect button, I did so too hastily, apparently. So it's saying, hey, couldn't open the device. But if you do it a second time, it should give you a list of microbits connected to your computer, of which we only have one. Select it, hit connect, and then that was download button changes to a flash button, and then the connect button changes to disconnect, in case you want to disconnect from the microbit. Okay, so let's look at the chat and see how it's going for whoever that was. Not getting flashing anymore. How do I reset? All works as you said, except when I hit flash, there is no action. Is there no, oh, okay. So I can think of a couple of explanations for that. One of them is there's no action on mine right now either. And the reason is because this program, which is a summary of the Python tutorials, only shows in the serial terminal. So it says hello, and then it prints some values, and then it says A is greater, counts to 10, or to 9 actually, and then it enters an endless loop. So hit open serial, and let's see if you get this kind of output. Got it? Okay, okay, good. So we're all on the same page here. Yeah, and that there's a big difference. I'm going to close serial. So here's the first one, print hello. Well, immediately after that, we could say display dot scroll hello. And double or single quotes are okay. Both will tell it that you're doing that with a string. So now when I flash it, we'll see hello scrolling across here. Flash. And notice that the second time it goes very quickly. And then, so there is the hello on the microbit. And then if we go to open serial, it's going to restart the program, which means that it'll display hello on the microbit again, but it will also display hello in the terminal over here on the right. And so the difference here is that print is what causes the microbit to send output, to send its messages to this terminal here. And display dot scroll, display dot show, things like that will send the same output to be displayed on the 5x5 LED matrix on the microbit. Okay, how's that for an explanation? Does that work? Okay, thank you. Thumbs up. Whoa. All right. Now, so very quickly, communication can be, well, sleep is something where sleep 2000 causes it to delay for 2 seconds. That's 2000 thousandths of a second, or 2 milliseconds, 2000 or 2 seconds, 2000 milliseconds. Print hello will put you on the terminal. Display dot scroll hello will put you on the 5x5 LED matrix display. Then the second activity is remember, and the very first part of that, we just, set A and B to a couple of different values, but I added in a few things, F for a floating point and T for some text, and you can actually display all those things. So that's why you see that on the terminal when we run it. Hello. And then B is greater, then it counts to 9, and then it says entering an endless loop. Here is our 1.414 and our text from right here, where we set the values of A, B, F, and T, which are all variables, and then displayed all of those. Calculate, just a simple addition. And then the if then, I want to emphasize that when you have a block of code like if, and you give it a condition like A is greater than B, and then have a colon, when you hit enter after typing that, notice how it automatically indents. And the reason for that is because it has to be indented in order to be executed as a result. So if this condition, if A is greater than B is true, then it'll display A is greater. Otherwise, it'll display B is greater if B is greater than A. And then the catch-all, if neither of those two are true, then it must be true that A and B are equal. So for example, we could change B to 2, rerun the program, the script, and then go back to open serial. And so here we have a low. It'll print our variables. And then look, A and B are equal.
I have a question.
Okay.
To slow down scrolling, do I enter delay? I'm assuming that's scrolling on the microbit.
Yeah, I'm assuming that's scrolling on the microbit too.
It might not be though. So if we can get clarification on that.
Okay.
Yes, on the microbit.
Scrolling on the microbit. Okay, so for that, see this nice question mark right here? What we can do is go to documentation and then do a search for display.scroll. I've done this before. It auto-filled. So display.scroll. And let's see here. I think microbit MicroPython API display, that sounds to me like documentation. So I'm going to open that one in a new tab, and maybe the hello world will end up saying something about it. So this is at microbit MicroPython read the docs. This is essentially where it takes you when you click that question mark and ask for documentation. Okay, so here is display. Yeah, no, that's kind of, I see we're in the developer guide. So let's try hello world. So here we're displaying, and it should talk a little bit later on about setting the speed. It didn't. Okay, I'm going to go here to display. And display get pixel, set pixel clear, show display.scroll right here. So see how it says that the first thing you can enter is the text. And then when it shows here, delay equals 150, that's the default. So basically, if you don't put anything other than the text, its delay is 150. But let's try adding delay equals 250 to our display.scroll. Flash that. Go back to open serial. Yeah, it looks slower to me. That hello does seem to be almost half speed now.
That is much better, easier to read.
Okay, so that's something you can always do, and I'm really glad you asked that, because we got to talk about the default parameters that we don't necessarily, that can be taken for granted. But there are additional things like that. For example, loop by default is equal to false, but you can make it true so that it just keeps displaying the same thing. And it talks about each one of these here. So for example, here is where it explains what delay is. And so that's the microbit documentation for MicroPython that you can use to look up for questions that aren't necessarily covered in the tutorial. I do believe that that actually does appear in our tutorial somewhere, but I'll have to get back to you on that. So what happens if I were to write down here? Can everybody see okay? Can you see my window all right? What would be the difference between adding a print statement Oh. If I'm going to use an apostrophe in my string, I need to use double quotes. Isn't that great? All right. So right now, if I run this program, do we expect to see A and B are equal? And then isn't that great, given that A is 2 and B is 2? Are we all on board with that? Okay. Now, what if I unindent it? Are we still going to see A and B are equal? Isn't that great? Okay, I see one no, and I see some pauses. Now, this is a trick question. Sorry about that, everyone. Right now, it's still going to print A and B are equal, and it's going to print isn't that great. But if I change A to 3 so that they're not equal, now it'll say B is greater. No, it'll say A is greater, and then automatically do isn't that great. And the reason for that is because when it's not indented, it's basically after the MicroPython runtime is done with all its decision making, the next thing it's going to do is the next non-indented thing. But if we indent it, it will only do it as part of the else condition. So now that I've made A and B equal, or not equal, I've made A greater, it's going to print this, and it won't print that. If I unindent it, it's going to print it regardless of which one of these is true. Okay, how is that? Are we clear on that now? Is that okay? All right, that's a very important lesson for the students as well. And it's similar for loops. In MicroPython, when you count through something, it's going to be inclusive, and you use in range. It'll be inclusive of the first argument, but it'll only go up 2, but not including the second argument. So you may have noticed that it counted to 9, and that's why. If you want to slow down the rate at which it prints, you can change the sleep command, or the sleep function call, and that will change the rate at which it prints inside the terminal. And then we have an example of an infinite loop. So these are all things. And before we take a break, what I want to do is just revisit the idea of saving a script. So this script, I think a good name for it would be the basics. So here is the script name in the upper right. And it's starting as microbit program. But what we want to do is we want to call it the basics. After naming that script, and again, this is a review of the save and save as and etc. So now we've named the script. If you want to save it, hit load save, and then select download project hex. And for me, it says the basics with a 4 in parentheses, because this is the 4th iteration of me saving the basics. Okay, so let me know when you've all got a copy saved. And again, that's load save, download project hex. So that's going to download your project. Excellent, thank you. 1 thumb up. 2, 3, excellent, very good, very good. I see, what is the difference between the project hex and the Python script? Right now, there's not a lot of difference. So you could hit load save and select download Python script. There are a few downfalls to this. The first is when you hit download Python script, your browser might warn you, mine did not, but your browser might warn you that you're downloading a Python script and it could contain a virus. So that's one downside, is that, we don't want, students' computers warning them about that. So Hex is a better choice because it'll be fine either way. The other thing is that, like if we take a look at, Cyberscope. Okay, so here we are at Cyberscope. We're going to download try-cyberscope.hex, and it downloads as a hex file. And then I want to open it up here. So I'll hit load save, click or browse for file. And then try cyberscope.hex is there. I know you might not, that's not going to, no sense zooming in on it. I just clicked try cyberscope.hex and I hit open. Okay, now the problem is if I were to save this as a plain old Python file, what I would lose is, in this case, the multimeter module, which is helping me out. So the multimeter module here is, you can find it in load save, show files, and then here's multimeter.py. And multimeter.py just has a bunch of extra code that the students won't have to write in order to get a multimeter display in their Cyberscope. And what happens is, right now, this code will run. I can flash it. And then I can go to cyberscope.parallax.com. I want to disconnect here, reconnect over here. And here it is. It's running, it's doing its thing. And part of that is it's getting some help from the multimeter module, which is a separate file. And that file is contained inside the hex file. So you don't have to re-add it every time. But if instead I hit load save and saved a copy of this as a Python script, it warns me. It says this project contains multiple files that will not be saved using this format. We recommend downloading the hex file, which contains your entire project and can be loaded back into the editor. Are you sure you want to download the file, the try Cyberscope file only? Sure, okay, I'll do it. But then if I open up that try cyberscope.py file and I go back into load save, I think I might need to imagine that I've come back on another day. So I'm going to reload the editor. Then drag and drop try Cyberscope in. And then take a look at load save. And oh no, I don't have that file to help me out. And when I try to connect and then flash this file, it'll seem fine. It'll definitely flash. But what'll happen is there's a frowny face that appears on my microbit. And if we look at Open Serial, it says that it, might need to do it twice. It says that it cannot find the multimeter module. Well, that's because it's no longer in my project. But if I go back to try cyberscope.hex, load save, or browse for a file, try cyberscope.hex, and open that. Now, if I flash it, it'll start working again. And if we look at the list of files inside the project, here we have multimeter back in the project again. So those are the two reasons that it's important to save as a hex as opposed to as just a python.py file. One is you won't get a security message, and the other is if you had any extra modules to help you out like multimeter.py, you won't lose them. So every time I save, I can say try Cyberscope modified, and I can then load save, download project hex that. When I open it, have to refresh here.
You are
So that-
definitely answering the question that was asked exactly. What is the difference?
Okay,
So there was one other point made though, that trying to open a hex file, say in Notepad, is not going to be readable,
yeah,
where
that's
a
a really
Py-
good point. And
whereas
for
a Python file is.
that is true. The hex file is not readable in Notepad, whereas the Python files are. Now, another thing is, and this is one thing I really like about the new editor, is that if we go to python.microbit.org/v/3 and open try cyberscope.hex in it, great. We have the user code that displays all that stuff. But if you go to the project button down here, you'll be able to actually look inside the multimeter module
Oh, nice.
and see the code that's in it. And from here, I believe you can also save the individual Python files for, examination in Notepad later. Not 100% sure about that, and I'm running short on time, so I don't want to try
Yeah, I
it.
just wanted to mention it's probably time for the midway break.
It is indeed. And so let's go ahead and take a 5-minute break. So it's 4:08. Let's Pacific. Let's come back at 4:13 Pacific time.
And I am going to leave the recording. So
And we can go ahead and take any questions or comments that anybody who's just sticking with us. Go get yourself a drink of water, use the restroom, etc. But if you're sticking around, you're also, please feel free to make any comments or ask additional questions that might have been a little off topic during the main presentation.
I have two questions.
Okay, go ahead, Justin.
One, I was in a Cyberbot training, and the kit that I got for this didn't include the battery, nor did the other one include the battery kit. It has like the circular one. So would I just be able to modify, instead of using the board, the Cyberbot cut down board, could I just use the regular board that comes with the Cyberbot robot, and use a separate breadboard, the one that it comes with? Does that mean?
Sorry, I'm trying to think here.
I don't think that is going to necessarily work because of the connections that are made to the propeller microcontroller on the Cyberbot board.
However, you can use the Cyberbot board to power your servo. So Justin, let's talk offline about that. I want to meet with you so that you'll be able to run your servo, because otherwise, without the 2-cell battery pack, we won't be able to test your servo.
Yeah, so I can just power it with.
You can use the 3.3V supply on your Cyberbot board. Basically, just at the 50,000 foot level, what you're going to do is you're going to run a wire from, maybe this is a little more zoom than 50,000 foot, but you'll be running a wire between G and D on your Cyberbot and the common ground, which I'll get to shortly, on the breadboard kit. And then you'll be running 3.3V from your Cyberbot to the servo's supply input instead of the way it's going to show you in the tutorials. And so with that, you'll be able to run the servo. And that's actually the only reason that we need the battery pack.
All right.
So,
fine.
yeah, if I don't remember to contact you, see, I'm going to put in here, follow up with Justin into the chat. With Justin about batteries. Okay, note to Andy. Follow up with Justin about batteries. Okay, so I put that into the chat as a reminder. Please email me if you don't hear from me by, say, midday tomorrow. Because what I want to do is just make the circuit real quick, take a picture of it. I'll send you the picture so that you'll be able to have it connected that way when you do your servo.
And
go ahead.
second question. I have the broken microbit, but I don't know how to get it back to you.
Oh,
There
they
wasn't
didn't send you a return envelope?
No.
Oh, okay. This one that you got the replacement of that one,
I did.
and it does work.
It does.
Okay, so yeah, I'll go ahead and email you when I'm following up about the because I don't think it's we may not need that microbit to look at why it failed. So I'll have to check on that and see if we need to send you a self-addressed envelope and get it back or not.
Okay. That sounds fine. I appreciate it.
Oh yeah, certainly. As long as you have a working microbit in replacement of the one that didn't work for you, that should be fine. We are definitely curious of why a microbit would end up not working. So some postmortem would be nice, but I'm not sure that we need it or we'll have the time to look at it. So I'll check on that and get back to you.
All right. Thank you so much.
4:14. Okay, time to restart. Ready, everyone? One thumb up. I think everybody's ready. Okay, there you go.
We have a couple missing. We have Bob and Sharon.
Oh, thanks, Ari.
We had a question about the cyberscope.
Okay, let me see if I can find it.
I paste the link to the cyberscope and how to get the code. The code can be, you can download the code from that page. So
yeah, so once you follow the link that Ari pasted in, which is cyberscope.parallax.com, it'll take you here, and then basically these are step-by-step instructions on how to run the demo no circuits required version. And then once you get here too, there's some slides, and you can advance to the second slide. And that second slide has a little video that I played earlier that kind of fast forwards you through just how to run this test code. And that was actually what we did for the homework. And so it is also on the homework slide, the python.microbit.org editor web USB tests. When you go there, it's right near the end, step by step. Cyberscope tests. So here it is in text. And again, that was from the pre-workshop homework slide. Right here. Okay. And then again, there's a more involved step-by-step video and document if you're interested in more attention to detail on each step. And with that, we are going to jump into the hands-on activities. Let me freeze my video here. Okay, hopefully that'll slow down my CPU fan. All right. I'm going to close some tabs too. See what else I can close here. All right. So the first thing that we're going to start with, just a bit more show and tell here, is this is this is after the prereqs. So if we back up just a little bit, go to the What's a Microcontroller List O chapters, you'll have gone through the writing microbit programs, which we were just talking about. Computer microbit talk goes into, so writing microbit programs uses the 5x5 LED matrix and lots of examples. Computer microbit talk has some examples of using the terminal, as we also did. So then we get to breadboard setup and testing. If you want to go back to the contents, you can always hit there's a go up link below the contents for the chapter. So I'll go ahead and share this with you just so that you can get to it if you want. Not required yet. Paste, send. All right, so this is where we're going to set up the breadboard. And some of you may be wondering,
What were you meaning to paste in there? You pasted a word or a sentence, but not a link.
Thank you, Stephanie. Yeah, I apparently shaded
Okay.
breadboard. So if I copy it now, or copy link address, let's try that
There we
again.
go.
Thank you.
You're welcome.
All right. So here's an overview, and every chapter starts with a what's it about. It's got before you start, and it talks about the hardware you're going to need and what tutorials you should have done first, and then what to expect to know after you're done. And as far as connecting to your breadboard, this kind of kicks it off right here. But what is a breadboard is where we start to talk in a little bit more detail. And there's always going to be an animated GIF if it's maybe a conceptually complicated thing. And so in addition to the animated GIF, in many cases, you may find yourself wanting to talk to the students about it. And so above the animated GIF, there's an MP4 link. And so we can stop at the MP4, or we could, unlike the GIF, you have some control over what plays and for how long in the MP4. So you can back up a little bit or scroll forward a little bit. You can hit play and pause. And so, for example, one of the things that you might want to pause on is, hey, students, look at this. We have a column with letters on the top. And so here's an example of column G, and we have a row, and then we have a bunch of rows with numbers by the side. And look at that, there's row 16. And so then what is the intersection of column G and row 16? Well, that's going to be a socket, G16. And remember that because the instructions are going to tell you possibly to plug something into G16. And also, backing up a little bit, it defines that these things with a bunch of rows of 5 sockets are called terminal strips. And then these columnar parts of the breadboard that you've got in your kit are called bus strips. And so there's a lot of good learning. And so the bus strip has a a positive or plus column and a negative or minus column. So that's some breadboard introduction that can be done. And that there is more breadboard introduction, but first we want this, we don't want to put it all in one spot. So we want the students to actually get their hands on something. And so this is another one where we have an animated GIF, and you're going to be doing this in just a sec. So what we want to do here is again, there's an animated GIF, or GIF is apparently the proper pronunciation of it. Is go to the MP4, because the MP4 is essentially covers, you can kind of go step by step and also read the checklist instructions. They're there as well. And so it's going to get it across in many different ways. And so you'll start with your microbit and end up fishing this other Edge IO adapter board out of your kit. And so what you'll do is you'll insert the microbit into the Edge IO adapter, set that aside, and then pull the breadboard out of your kit and check to make sure it's right side up. You want to have the numbers 1, 2, 3 in the top left. And then of course the larger numbers up to 30 on the bottom left. And then you can put the board over it. And what you want to make sure is that the bottommost pin on the Edge IO board is plugged into the bottom left socket on the terminal strip. So that's going to be A30. So here already we're using the coordinate system that we just talked about. And so we made it translucent so that you could see where the pins that stick out of the bottom of the Edge IO board get plugged into the and so it really tries to give us as much resource as we can so that the students don't misstep, like there's another pair of pins that are going to go into this bus strip. And so after the students have checked to make sure that they've got it lined up but not necessarily inserted, then it shows to actually, now that everything's lined up, push those pins all the way in. So see how there are some pins sticking out underneath the board? Those need to sink all the way in so that just the little plastic headers are all that's left and the rest has sunk into the breadboard. And then it'll look like that and we'll be ready for the next step. So go ahead and do that. You'll need your breadboard. So here's the breadboard. And then here is the Edge IO board. It's plugged into some black anti-static foam. Just go ahead and pull that downward and away from the Edge IO adapter, and you'll see those pins that are sticking out underneath. Then we will make sure that we have 1, 2, 3 up top and 28, 29, 30 down below. And we'll make sure that we've got the pins. So the P0 pin on the Edge IO adapter needs to plug into A30. And then there'll be these pairs of pins that plug into the bus strip. And then after checking that the pin below 3V plugs into A12. So you've got P0, oh, how about A11? Yeah. So you want 3V, the 3V pin in A11, and the P0 pin in A30. Once you've got all that, and it looks like that from the side, go ahead and press firmly, and it'll sink in all the way so that just the plastic headers underneath the Edge IO board are all that's left. And then I kind of skip the step where you firmly insert the microbit into the Edge IO adapter. So that's what we want when you are done. And go ahead and give me a thumbs up either.
Here's a question.
Okay. Does the
Um,
adapter need to go back into the anti-static bag? I got a toolbox for all components that has a little space for it. It fits in the bag. You know, when you're done with it, I don't know. I usually leave mine just all connected like so. And then I typically end up disconnecting the USB cable. And I'm gonna upend the box that all my stuff came in. And so if you don't have a plastic box, or even if you do, normally I would store it just complete like this. Doesn't quite fit. Yeah, it does. There we go. So I usually store that, and then there's going to be a bag of small parts. And I keep those small parts, any that are not in use, I keep them in the Ziploc bag so that they're not floating around. And then there's going to be the alligator clips, the servo, batteries and battery packs. So that's normally the way I carry it around, is just, you know, in the box it originally came in.
There's a question about, is there anything you shouldn't be touching or putting too much pressure on? Apart from being careful not to bend any of the pins.
Yeah, so the most common piece of advice, and I believe we adhere to that in the step-by-step part of the tutorial, is that you basically want to have the USB cable disconnected when you're making changes to the circuit. You also want to have the battery disconnected. So when you're making any kind of circuit change, that's an important step. And then, you know, if you plug it back in and then suddenly nothing at all is working, well, unplug it and start looking for mistakes in the circuit.
Since that connector is difficult to unplug and plug where the battery goes, I've seen people choose to pop out a battery.
That's a good point, Stephanie. And also the microbit actually comes out pretty easily. So you can just set aside the microbit and then work on the circuit here.
Well, that if you don't have the battery pack connected. If you do have the battery pack connected, that's not going to. It'll protect your microbit, but it won't necessarily protect the circuit from itself.
Yeah. So here we have the battery pack. And yeah, if you've got an application with the battery pack and it's plugged in, what Stephanie is saying is that you can slide down the lid of the battery pack and just remove one of the batteries, and then or both, and then you have disconnected power. Okay, so have we all got this? One thumb, thank you. 2, 3, 4, 5, 6, 7, 8, 9. All right, looking good. Okay, I think we're ready to move on, but feel free to either unmute or chat for another minute if that's what you need. All right. So the first electrical connections we're going to do is basically, so that was the first activity, is connecting the microbit to the board. The second activity in this chapter is making and testing electrical connections. And so this is where essentially, if you put 2 wires in the same row of 5 sockets, the microbit is going to tell you that it's electrically connected. Whereas if you put it even 1 row down, it won't be electrically connected. And so we again try to support this with lots of good visual stuff, like showing where the interconnections live underneath the breadboard, and how to pick a row. And this is definitely one that I like to, if I'm speaking with students, I'll say, all right, so we've talked about how one row of 5 is all electrically connected underneath, and actually I believe that where's the picture of that? How it works? Okay. I know I have a picture of underneath the breadboard and the yeah, I'm sorry. I don't remember where I put that. But regardless, when you're connecting 2 wires, I like to go through with the video and talk it through and say, okay, so what if we have a row of 5 sockets? Well, guess what? If you put 2 wires in that row of 5 sockets, they're connected. Now, if you add a 3rd wire, even if it's only 1 row below, is it going to be connected? No, it's not. And then we can start going through and continuing to add wires and ask the students, okay, which ones are connected and which ones are not. And so it turns out that the 2 lower wires are connected because they're in the same row, but not to the wires immediately above. And then the 2 upper wires are connected because they're also in the same row. Okay, well, now we're in the same row, but it's a row of 10, not a row of 5, and the rule is row of 5. So each of the rows of 5 are still connected, but those are different rows of 5. And so are those. But you can even add a jumper wire across, to connect one row to another. And then guess what? They will be connected. So that's a quick how-to on how to connect wires together with a breadboard. And after that how-to, what we're going to do is build what's called a continuity tester. And a continuity tester is a device that's typically part of a multimeter. And multimeters are used to measure continuity, voltage, resistance, and current, and several other things. And so your microbit multimeter is going to start by inserting 2 3-pin headers into the board, and then grabbing a hold of a red and a black alligator clip, and then use the alligator clip part to grab red and black wires at one end, and then the 3-pin headers that you inserted into the P2 row and the P0 row on the other end. So let's go ahead and try that. I'll show you real quick. So your 3-pin headers are going to be in this bag of parts. And they look like this. So there are 2 3-pin headers. And what you'll do is you'll put one on the bottom left row, CDE columns, and then skip a row, and then add. So basically, row 30 and 28 is where you're going to plug the 3-pin headers. And then you'll have some alligator clips and some wires. So you'll need to grab one red wire and one black wire. And then get your red and black alligator clips. Untying the knot first. Red and black alligator clips. Here they are. And then the black alligator clip, you want to grab a hold of the lower 3-pin header. Normally we'd be disconnecting power, but we're not going to hurt anything if we don't in this case.
But here's a question. What happens if the alligator clips touch each other near the 3 pins?
Well, you might get a mistaken measurement. So there are ways, and this question has come up before, so I should probably put an alternate wiring diagram. Some teachers prefer to have the alligator clips further apart. But these two guys should not really run into each other if they're connected, as you see here. It is possible to take this 3-pin header. I'll just put in a different 3-pin header elsewhere, maybe up here.
Hey, what I did was I put the black alligator clip towards the bottom of the 3-pin header, and the
Oh, that's a
hot
good
I
idea.
put on
Yeah.
the top of it.
Okay.
So that way they're not touching each other.
Yeah, so I could probably just take a photo of this and put it as an alternate example where you'd insert a red wire into a socket. So that also would work. If there is a concern, but normally, I mean, there's not any way to damage anything because the measurements are basically the microbit is going to be monitoring, but not trying to supply current to these pins. So you'll be fine. You might get a measurement that's incorrect, but that's all that could happen. Okay, so now we have our little meter all ready to go. And let me actually paste a link to this MP4. Sorry, I should have done that. Okay, I should have pasted you a link to what we were looking at here. Okay, that's the page I'm working from. And I'll open the MP4 and freeze it on the finished circuit. There we go. That should be nice and visible. All right, folks. How are we doing? Thumbs up, thumbs down. Up, 1, 2, 3, 4. Oh, you guys are great. All right. Well done. Okay. So now we're ready to take some quick continuity measurements. And by the way, this slide right here, I'm basically going through the learn.parallax.com tutorial excerpts. I should be methodically going through here. So we are at parts and circuit. And so the next up is script and tests. So for the script, you can also just go to the previous and next pages, as well as you've got your contents right here. So the script follows the parts and circuit. And watch carefully. There's continuity tester.hex right here. The checklist instructions go through all this, and there's also an animated GIF that shows it. You'll want to right click continuity tester.hex and select save link as. And then it'll let you download the continuity.tester.hex. So remember, I'll give you a page and we'll have you right click continuity tester.hex and download it. After downloading continuity tester.hex, you can hit load save, select or browse for file, and then it should take you to your downloads where you can select it and click open. And then if you're not connected, hit connect, and then hit flash, and then hit open serial. Actually, you don't need to hit open serial for this. Sorry about that. So I'll run through that again. You'll hit load save, select or browse for file, go find continuity tester.hex, select open, and then make sure you're connected, and then hit flash. And then take a close look at your microbit. It should have, if your wires aren't touching, it should have a circle with an arrow through it. And that's indicating not connected. Now, if you touch those two wires to each other, you'll have a beeping sound. And you'll also get a check mark on the 5x5 display indicating that it's connected. Everybody good with that? One thumb up. 2, 3, 4, a thumbs up. 5, 6, 7. All right. 8, 9, 10, 11. Okay, excellent. So now we can see, electricity, when you have two wires up against each other, electricity can flow through that circuit. But if there's an air gap between the two wires, electricity can't flow, so there's no continuity. You touch the wires, there is continuity. Now, here's the thing. If you pick a row of 5 sockets, and then some other row of 5 sockets, you're not connected, there's no beeping. But then, if you plug it into the same row, you should see the check mark and hear the beeping, indicating continuity. So try that. And in this case, you don't even need to plug the wire all the way in. Like, you can just basically touch the two probe wires to any socket in the same row of 5. And if everything's nice and connected, you should immediately get the beeping and the check mark. And then as soon as you unplug or probe a different row, we get not connected. And it's only when you get any socket in that same row that you'll get the connected signal. Okay, is that working for all of you? Excellent. Okay, thumbs up are coming through. Great. All right. So now we'll skip doing all the different combinations, but I think it is helpful for the students. So we went through the how to connect 2 wires video, and we saw okay, so here we have node tests. So the students will actually go through and they're going to try all the ones we talked about earlier. So all the different combinations, and notice that I have kind of a close-up view of where the wires, which socket those wires are going into. And then they can probe more different combinations on the board. Okay, so before the day's up, we want to set up power and then make sure that our power works. So for power, we're going to need 2 black wires and 2 red wires. And I'll go ahead and zoom in on where those will be connected. There. How's that look? Is that fairly clear? I'll also paste in the page for you. So just grab 2 black wires and 2 red wires. The black wires should connect sockets in the negative columns of the bus strips. Those are those long strips between the terminal strips. And the red wires should connect the 2 positive sockets. So you want to, for the black wires, you want sockets next to the blue vertical stripe or next to the minus sign. And for the red wires, you want one to connect the middle to the right bus strip, right by the pluses. And then you're going to go from 3V, that's row 11 on the breadboard, to the plus column, anything on the left right by the red line, the red vertical line. Be very careful with this. And this is one where it would be a good idea to temporarily disconnect or pull your microbit out of its socket while you're doing this. There. I bent the wires over. Usually I bend them more above the board, but just to make it clear on the video, I bent them one up and a couple down. That's true. It is a rather, I see a comment that one of the teachers thought she lost audio because everybody's being so quiet.
Sign of productivity.
Yes. Yes, much better than crickets, though. Yeah. Okay, so have we got power wired up? Thumbs, please. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 11, 12. Okay. Oh, looking good. All right. I think we're safe to move on. As always, ask me to hold up if you need a little more time. Okay, so now what we're going to do, probably the last thing of the day, is to use a voltmeter app to just test the voltage.
Wait, one more question before we move on.
Oh yes, of course. How do I get power? Just plug the microbit back in. Yes, that's correct. So now we'll want to plug the microbit back in and actually kind of keep an eye on the lights as you do so. So when I plug the microbit back in, I want to make sure it's well plugged in. You want to see less than half circles at the edge of the adapter socket. And then we also want to see either the connected or not connected still displaying here. If this goes out, it might mean you have a circuit or error, in which case immediately unplug the microbit. If your continuity tester program is still running and still showing you continuity, then, or lack of or existence of continuity, then you're good. This is the fast forward version. There's a lot of double checking that happens in the student instructions. And then we're going to have you download measurevolts.hex. Okay, I'm pasting in the instructions for downloading measurevolts.hex. There we go. So we want to right click and select right click measurevolts.hex on the page I just pasted in. And then right click measurevolts.hex, select save link as, and then hit save. And it's going to appear in your downloads. And then after that, you'll want to go to your python.microbit.org editor, click load save, or browse for a file. Measurevolts.hex, open. And again, because this has the multimeter module in it, we really need the hex file in this case. And then as soon as you've got measure volts open, go ahead and connect and then flash. And then actually hit open serial. And right now, my wires aren't connected to anything. So that's why we see kind of a floating minute voltage measurement. So let me know when your voltmeter program's running. Thumb up, 1, 2, 3, 4, 5, 6, 7, 8, 9. Still waiting for a few more. 10, 11. I see a not yet. Good. Okay, so let's see. Thank you. Okay, thank you. The not yet is now ready. Perfect. Okay, so now that we've got our voltmeter up and running here, should be displaying, hit the open serial button. It should display the voltmeter measurements. And then we have, instead of a continuity tester, this is all in the tutorial, by the way. Again, we're doing the fast forward version here. So what I want you to do is pick any socket next to the blue vertical line on the right and plug in your black probe, and then pick any socket next to the red line on the left and plug in your red probe. And what you'll want to see is something in the neighborhood of 3.3 volts, plus or minus maybe, I don't know, 0.05 volts. Let me see if I can get you a better close-up of that. 3.28 volts, excellent. I got a text with that value, so you're right. Mine's 3.29, 3.28. It's close. 3.3. All right, WB.
Yeah, 2 exact 3.3s.
Thumb up. Now, you would also want to see 3.3 volts if you unplugged from the bus strip on the right. If you just took the red probe and went for a red socket in the center bus strip, you still want to have 3.3 volts. When you unplug it, it should snap down to almost nothing. Well, 0.64, not sure why. But if you plug it in, we want to see that 3.3 volts again, even though you're in a separate bus strip. And the reason that should work is because we have these wires up top that are connecting all the bus strips together. So we have actually the right 2 bus strips should all have 3.3 volts. And then the leftmost bus strip is not used until we plug in the battery pack later on. Real quick before we talk about the homework, I'd like you to just try one thing, which is to hit close serial. And then, oh, by the way, I'm sorry. So are we all good with our 3.3 volts? Okay, excellent. Good job, everyone. What I'd like to do is just test out our cyboscope for measuring this. We did this in the terminal, but let's try changing terminal to cyboscope. Capitalization will not matter. Unless you have a little bit of OCD like I do. So change it to cyboscope and hit flash. So we're changing terminal to cyboscope and then hitting flash. Now, if you open serial, you'll actually see a much less human readable version of the voltage. And what you're actually seeing is the voltage and the number of milliseconds that has elapsed in something called a dictionary. So this is what gets sent to the cyboscope. Once you've seen that, hit close serial. We don't need to see it that way. And also hit disconnect. Then go to cyboscope.parallax.com in a new tab. So basically hit the plus next to your Python editor tab and you'll get a new tab. And I'll paste cyboscope.parallax.com into the chat as well. Copy. Paste. There you go. And try hitting connect and selecting your microbit. And hopefully you'll get a nice, beautiful voltmeter display. Of your voltage. Excellent. Thumbs up. I see the thumbs coming. Looking great, everyone. Okay, so this is what the students go through, and it's kind of nice to have them testing step by step, making sure all the subsystems are working before they start building their circuits. And along the way, they learn how to take voltage measurements. They learn how to take continuity measurements. They learn how a breadboard works. Lots of good stuff. So for homework, and I'm going to email this to you as well. For the homework, what we're going to do is I'm going to have you follow along at home. And what you're going to do is your first breadboard circuit. Very simple one. There is a catch, though, which is that this light right here, you have to make sure to plug in the shorter pin here on the right side, and then the longer pin here on the left. And if you do it that way, and you grab a red, red, brown, a resistor with red, red, and brown stripes, and a gold one too, and you'll be following along. That the instructions are gonna be very methodical, so you'll be able to just follow along and build up this circuit. And so it'll start with, hey, here's what all the parts look like. Here's what the little striped bands on the parts look like. And that's why we're going to need a magnifier, is to tell apart a red, red, brown resistor from a brown, black, red resistor, for example. And so you'll be grabbing all these parts and you'll be following along with the checklist instructions, and you'll be making sure you've got this, and then you're going to build the light circuit. Okay, so you're going to grab the parts it calls out, and it'll show you how to add the wires and the LED light with the longer lead on the left. And when you plug in the USB cable after building the circuit, the power or the light should come on. So here's plugging it in power wise, and the light will come on. So we'll have you do this. And then there's going to be a quick using the voltmeter to measure the voltage across the entire circuit, and then across each little piece of the circuit, that being the light and the resistor. And the voltage across the light and the resistor should add up to the total voltage across the circuit, plus or minus, 0.01 or 0.2, 0.03 volts. So that's going to be one thing. And then I'm going to have you, after you get that one LED circuit built and tested, we're going to have you note how to plug in a push button. So here's a close-up, and I'll include links to this in the email. And then after that, we'll have you build up a master circuit for our first few applications on Wednesday. And again, I'm going to email all this to you. So first, it's just connecting one light, measuring the voltage across it, and then we'll have you connect a bunch of lights. When we come back on Wednesday, we'll make sure they all work. We'll have to do a little bit of troubleshooting. There might be like a light not plugged in all the way. You want all these leads to always sink in by, say, 1/4 to 3/8 of an inch. Yeah, that should be right. Yeah, 1/4 to 3/8 of an inch. So they want to sink in, nice and firmly into each socket. And also often there are bomb site errors, as in, you might be a socket or below, above or below where you intended to be. So we'll need to clean up some of those things on Wednesday. So get one light working, test the voltages on it, and then build up 3 lights and 2 push buttons, and we will reconvene on Wednesday. And again, I'll send that all out. We'll also be sending a link to the YouTube recording, so you can refer back to whatever you might need to. And with that, I think we are ready to. I also included the schematic, but the wiring diagram will probably be easiest to work from at this point, especially if you're not familiar with schematics yet. We'll talk about that on a little bit more about that on Wednesday. And with that, I think we can go to the questions and answers and tech support portion and end the recording.
Okay, I will stop the recording, and if you don't mind, I will hand host back to you.
Okay, feel free to stick around, everyone. But thanks. If you decide to sign out now, thanks for coming, and we'll see you Wednesday. And check your email for homework and the YouTube link.